Thanks, Radhika. So let's begin by thanking our organizers, Radhika, Gupta, and Suraj, Krishna, and our host ICTS TIFR for this conference. We'll start off this week with a lecture by Professor Genevieve Walsh from Tufts on ℓ2 homology and boundaries of infinite groups.
Hi, can you hear me? Okay, just tell me if you can't hear me or if you can't see what I'm writing. It's really nice to be in India. It's an amazing country. Thanks for inviting me. I see that there are many experts in the audience, and I'm going to start off very slowly. So I apologize. And then the more people that ask questions, the better the talk will be. So if you want the talk to be better, ask more questions from different people. Okay, so please ask me many questions. Okay, so we're going to let X be a proper geodesic metric space. And G is going to be a countable group. Okay, and G acts on X geometrically. So these are the basic objects I'm going to be considering. If, I'm going to write too big, so this is the definition. So G acts by isometries. G acts properly discontinuously. So this means that the number of G such that GK intersect K is not equal to the empty set is finite for any compact set K. I won't write that. So it just means things don't bunch up against each other too much. And co-compactly. So this just means there's a compact fundamental domain, or when you quotient out your space by the group, you get a compact space. Okay, so we're going to be considering geometric actions. So here's some examples of some groups I'm going to be considering that I'll try to use later. So for example, the free group acts geometrically on this space. I'm going to try to use this colored chalk. So I can label these points, but I don't know if Indira did this in our talk yesterday. Did you do this one? I can label the points of this infinite telephone pole. Okay, so these are all going to be A's. And these are all going to be B's. Keeps going. How many of you have seen this before? Has everybody seen this before? I know you've seen it before. Okay, good. All right, so this free group, the group generated by A and B with no relations, is going to act geometrically on this graph. So that's an exercise. If you haven't seen this before, just think about it. It's going to, the A is going to move everything this way. This whole line will get moved here. And the quotient will be co-compact. It'll be the familiar figure 8 with fundamental group, the free group. Okay, that's one of our key examples. Another key example is going to be reflection groups. It might come up somewhere else. So given a graph, I'm not going to define a whole right angle Coxeter group. Given any graph gamma, I can find the right angle Coxeter group G of gamma, okay, where I just take the group that is generated and also I want to have the relations. So I have each generator has order 2, and then the generators commute exactly when there's an edge between them. Equals BC. equals CD equals DE equals 1. So this presentation for this group. Okay, everybody okay with that? So I can do this for any graph. I want to find the whole thing. I just want to give an example. So I take a graph and I can make a group where the generators correspond to the vertices. Each vertex has order 2. That's what these relations are for. And that's just an and. There's a 1, 2, 3, I'm missing one. Okay, so I have a relation for each edge that means that 2 generators commute. Okay, so this is in general the right-angled Coxer group, sorry. Angle Coxer group on my graph gamma. This is a great source of examples. These are also a great source of examples, as I think we'll hear about some later. Okay, so this group acts geometrically on H2, which I'll describe in just a second. Okay, so I can do some 1, 2, 3, 4, 5. Okay, so this is a hyperbolic pentagon. Okay, this is H2, which I'll describe in just a second. Okay, so I can think of H2 as the unit disk. So this is the unit disk with the metric in R2. Okay, and with the metric, the metric isn't so helpful. It's nice to see. So the ds equals 2 over. So this is just scaled. This is just the Euclidean metric scaled by the radius. Here's another model over here, H2 in the upper half space model. Okay, where here's some geodesics. And my metric is, yes, equals dx squared plus dy squared all over y. Okay, so let me just talk about these for just a second. Okay, so there's a conformal transformation that takes the upper half space here. So this is all the x, y in R2 such that like y is greater than 0. Okay, so this is upper half. It doesn't include this space right here. That's the boundary. And in this case, the geodesics are parts of circles that meet this boundary perpendicularly. So those are the geodesics. And that includes they'll look straight to the Euclidean eye when they're antipodal. Okay, so these are the geodesics in this space. These are some geodesics. And then I've made a geodesic pentagon here. Oh, I'm running out of colors. Okay, so now what does this have to do with this group? I'll just make some of them green. Okay, so this is a geodesic pentagon. It's bounded by geodesic sides. And I can make one so that it has right angles here. This is a right-angled hyperbolic pentagon. Okay, so that's why the name right-angled Coxeter group comes. And I can take this group, so this group G of gamma, this particular one, acts geometrically on H2 by reflecting in the sides of these and then composing these reflections. So I'll get a whole tiling of H2 by hyperbolic pentagons, which you might have seen before. Okay, so G of gamma acts geometrically on H2. Okay, and as an exercise, you might want to take this group, exercise G of gamma contains a surface group as a finite index subgroup. Okay, so the surface groups also act geometrically on H2. Okay, any questions about that? Don't fall asleep. Okay, all right, so now what we're gonna try to do is generalize the situation. So in one thing that we have in H2, so let me draw a geodesic triangle in this space that is an ideal triangle, meaning all the points are at infinity. We can only have that in hyperbolic space. So here's an ideal triangle, all the points are at infinity. And as you see, the neighborhoods, the way this metric is scaled, this metric is scaled with respect to height, this is going to be a constant distance neighborhood of like this geodesic right here. Okay, and here's a constant distance neighborhood of the other one. And then here's a constant geodesic neighborhood of this one. It'll look kind of like that. And you'll notice that I can find constants that'll make these two neighborhoods cover this third side. Okay, so this is what we say is this is an example of the delta hyperbolicity of this space. So, did I say hyperbolic space? So hyperbolic space. This is going to be a geodesic metric space. Where every geodesic triangle is slim. Okay, so that means, I'll just draw the picture for you. If I take a neighborhood of 2, that means there exists a delta such that the delta neighborhood of 2 sides contains the thirds. Okay, and you can see that this is not a proof because I haven't given you you can turn this into a proof by taking a geodesic triangle and kind of putting it in here, a finite geodesic triangle. You can turn that into a specific proof. So I sort of outlined the proof for an ideal triangle, but actually the regular geodesic triangles that are not ideal are delta hyperbolic. Okay, and this space here is 0 hyperbolic. And it's delta hyperbolic. These are both really good examples of delta hyperbolic spaces. Okay, so what is the boundary? Okay, so I can't cross that line. So eraser. I like these boards that are really long because you can't get tied up with there's a lot of fun that can be had with that though, but it's generally not good. Okay. Okay, so with the boundary of a hyperbolic metric space, let me switch to white. Is white better? Everybody's awake, but they're not telling me if white is better. White is better, okay, good. So let me say what the boundary of a hyperbolic metric space is. Okay, the boundary of a hyperbolic metric space. X. Okay, so this is just going to be, there's many different definitions. I've just given you one. Geodesic rays from some point, which I'll call 0 and X. Okay, and I say they're equivalent if they're at bounded distance, bounded Hausdorff distance. Okay, so let's think of some rays in some of our spaces here. For example, I could look at this ray. I'll take this as my origin point. Okay, the homeomorphism type won't change if I take a different point. So these are all different little things to prove. So here's a ray that goes out, keeps going out, getting farther and farther away from the origin. Okay, it goes out, and I can call this point like A infinity maybe. Okay, so This one doesn't have geodesic rays, but I could take a space, which is quasi-isometric to it, which I'll explain what that is in a second. Take this red. Take another space that went like this. This is another space that the F2 acts on geometrically. It's totally fine. It's still a geometric action. And I could take this ray that was like red. Okay, so those would be the same rays because they never go without their bounded Hausdorff distance to each other. So they define the same point at infinity. Over here, and I'll say what the topology is in a second. And over here, I can just look, and I already kind of drew the boundary at infinity. Okay, for hyperbolic space, we sort of start with the boundary for H2. So we sort of like think of it already as a boundary, which is fine. Okay, they're just rays at infinity. And here, these are conformally equivalent. This boundary is going to be this plus another point at infinity, which is sort of random. Okay, and what's the topology on this space? The topology is rays are close, so equivalence classes. Close if they stay close for a long time. Okay, so let's look at this space. This is a good one to do. So this blue ray all the way out to infinity and the pink one out to infinity, they're defining the same point because they stay close forever. So these points, if I go straight up, this is not close because they don't stay close very long at all. Okay, I could go out here for a long time and then go away from it. Okay, so my neighborhoods of this point at infinity are going to look like how far I stay right along this geodesic or this pink one. I only really have two choices for this one, pink, blue, and I could change pink, blue, it's fine. And then at some point I diverge and I'm not in the same equivalence class, but I am kind of close to it. And the farther out I go, the closer I am. Okay, so an exercise with this somewhat vague definition, okay, is show that the boundary of this, I'll just say this tree, is homeomorphic to the Cantor set. Okay, so you can think there's like 4 different ways to go here, right? Then I can go here and there's like 2, 3, you can start dividing up. It's pretty fun. All right, so you might want to think about that. Okay, and over here, the topology is exactly as I've already drawn it because I already thought of it that way. Little neighborhood. So these are going to stay close for a long time and then kind of diverge. You can take 2 deltas, how close they have to stay together if you want. Okay, questions about that? Okay, great. Okay, so here's some magical facts about the boundary. The boundary is very useful. People have, I'm gonna get rid of, I'll just go, I won't do anything fancy. So the boundary is a really useful topological, so now we have a topological space associated to just the boundary to dx. So definition, if G acts geometrically on X, this is just for a hyperbolic metric space. You can define a lot of different types of boundaries that are really useful. X hyperbolic, then the boundary of G is defined to be the boundary of X. Okay, so as I just erased, there's different spaces that a group can act on geometrically. Okay, so this is okay. Okay, and I'll explain why that's okay. So if G acts geometrically on many different spaces, they're all going to have homeomorphic boundaries. Okay, so that's why this is okay. So this does not depend on S. So let me just say why. Okay, and the reason, the real kind of deep reason, this is because both hyperbolicity and the homeomorphism and the boundary are quasi-isometry invariants. Okay, so let me just say what that is. That's why this definition is well defined. Okay, so what is a quasi-isometry? Okay, so throughout I'm going to have, these are metric spaces. Okay, so F is a quasi-isometric embedding. If there exists an A bigger than 1 and a B greater than or equal to 0. Okay, so isometry would be so sorry. Let me give myself some more space here. Okay, so a quasi-isometry is just a coarse isometry. So isometry would say the distance between x prime, would be less than or equal to the distance between f of x and f of x prime, which would be less than or equal to the distance between. Okay, so this would say my map was an isometry, right? Because they would be equal. And this just says I could change this by multiplicative and additive constant. Okay, so this is a quasi-isometric embedding. And then so we say it's a QI if it's both a quasi-isometric embedding and also is coarsely onto. Okay, so this just means that I'll just say Y is contained in a neighborhood of C of the image of X. Okay, so it might not go all the way onto, but every point in Y is a finite distance from some point in the image. So you can take little blobs over all the images and it'll cover the whole space. Okay, so this is a really useful key concept which will come up. Let me just say a few things about it. Okay, so G acts geometrically on X and G acts geometrically on Y. This implies that X and Y are quasi-isometric. Okay, so now we can say two groups are quasi-isometric. So this is a quasi-isometry is an equivalence class on metric spaces. Okay, so then we can say two groups are quasi-isometric. If G acts geometrically on X, G prime acts geometrically on X prime. These are all geometric actions. And X prime are quasi-isometric. Okay, so now we can talk about equivalence classes of groups. Very handy. Can't cross that one. All right, so here's some facts about quasi-isometry. So if G is Qi to G prime, and G is hyperbolic, so is G prime. Okay, so that's why this is what I meant by saying hyperbolicity is a quasi-isometry invariant. Okay, if G and G prime are hyperbolic, or one of them is, the other is, and G and G prime are quasi-isometric, okay, then their boundaries, so their boundaries are well defined by what this other stuff I just said, then their boundaries are homeomorphic. Okay, so this is really handy. So it's a really interesting question to understand which groups have what particular boundary. So take your particular favorite boundary and try to figure out which hyperbolic groups have that as a boundary. That's a hard question. It's known for example, groups that have a Cantor set boundary are virtually a free group. I'll say what I mean by virtually in a second. Groups that have a circle boundary. So this boundary, which I just erased, but it was right there, the boundary of H2 is S1. If you're a hyperbolic group with S1 boundary, then you're virtually a surface group. So this is but it's not, the converse is not true in general. There's examples of groups where, for example, there's the Bourdon buildings with a Menger curve boundary, even one-dimensional boundary, that are not, they have homeomorphic boundaries, but the groups are not quasi-isometric. So that's important to remember. Okay, however, there is a metric on the boundary. Let me just put this here. So you can fix this a little bit. Okay, so I'll just draw it with H2 because that's sort of the easiest. So the distance between 2 points on the boundary is going to be similar to a to the negative L. I'll say what I mean by that in a second. So this L is just the distance between some point and the geodesic between ZW. Let me draw this here. I have 2 points on the boundary, Z and W. And I'm going to pick a base point. The metric will change a little bit with a base point. Okay, and I'm going to look at this distance here. This is my L. Okay, so it scales like this. So as this L gets longer, these points get closer together. Okay, so that's consistent with this. And then I just have this is what I mean by it's approximated by this. But it's okay to think of it this way unless you're doing very specific computations. Okay, so you can sort of think of it this way. You can look at how far away the geodesic is between the 2 points at infinity. This is called the visual metric. And there's a whole family of visual metrics, as I can change this base point as I move around. Okay, and then, so I'm writing something related on the other opposite side, but I want to stay organized because I'm still a little frazzled. Okay, so if I have Z and Z prime are metric spaces. So that makes that space, those boundaries into a metric space. We have an N quasi-symmetry, eta quasi-symmetry. So we have, this means that I take 3 points, Z1, f of Z2, all over the distance between f of Z2 and f of Z3. the center is Z2 eta times the distance between Z1, Z2, the distance between Z2, Z3. Okay, so increasing homomorphism. Okay, so there's a finer quasi-symmetric or quasi-conformal structure on the boundary. And if the boundaries of let's see, the boundaries of X and the boundaries of X prime are quasi-symmetric, okay, or quasi-conformal, there's different ways you can say this. I'm just saying it once, so you could get the idea there's a finer metric structure on the boundary that does tell you the quasi-isometry. Then X and X prime are quasi-isometric. Okay, so the boundary, if you look more closely at the boundary, you can tell the quasi-isometry class. And let me just mention a few other things you can tell from looking more closely at the boundary. Yeah, question? F is the function, yeah, F takes Z to Z prime. And then there's another, this is just an increasing, yeah, thank you. Oh, F, yeah, thanks. Good. I can get you to ask questions if I make mistakes. Yeah. What is what? A is just some constant. You could take it to be, you just take a constant. Yes. Okay. They'll be quasi-symmetric, yeah, so you get different. Okay, good questions. All right. All right, now what am I doing? Okay, so just some facts about the boundary. That's why you might find this useful. Okay, so if the boundary is connected, then the G is one-ended. It has no cut points. These are all completely non-trivial things to prove. It's locally connected. So this is not true for other types of boundaries, which I'm not talking about, like the boundaries of relatively hyperbolic groups. They can have cut points, for example. And if it has no local cut points, so this can happen. So it's a local cut point. It's if I remove the point, I'll have more than one end, the local cut point. This happens if and only if G does not split over a two-ended group. Okay, so they can tell you about the algebraic structure of the group too. This is also some algebraic structure. Okay, and then also if I just have a group, I look at a group acting on its boundary, so it has nice dynamical properties too. G acts as a uniform convergence group on its boundary. So this means is many equivalent definitions. That is, G acts, well, I won't put a metric on it yet. It means G acts properly discontinuously and co-compactly on the space of distinct triples. So this is just like X y, z. So x, y, and z are all on the boundary. Boundary z, g, and x is not equal to y is not equal. None of these are equal. So this is a topology just as a subspace of the product. Okay, so you can look at the group acting on that. That's a nice space. So even just if you have the boundary, you can get a nice space for your group to act on. Okay, so let me get back to QI for a second. So this finer structure on the boundary will tell you about QI. Just let me say a little bit about quasi-isometries because they're so important and interesting. Okay. So here's an easy way for groups to be quasi-isometric. So remember, two groups are quasi-isometric if they act geometrically on the same space. So if I have H prime subgroup of H, okay, so I'm going to use this little notation that I kind of like. This little dot here is going to mean it's a finite index subgroup. H prime is a finite index subgroup of H. Okay, so to see this, I can just look at the Cayley graph of H, which I drew for F2. And then I can look at H prime acting on it. The quotient will still be by isometries. It'll still be properly discontinuously, and it'll be co-compact. It'll have a bigger fundamental domain, but it'll just be the index of the group size bigger. Okay, so that's an exercise to show this. And then another way is I could say H prime equals H mod F, where F is a finite group. So if I have a finite normal subgroup, okay, here I can have H prime act on the Cayley graph of H where F just acts trivially. Okay, so these are two ways to get groups that are quasi-isometric. And so we say that, so always we're going to have this. So it's never going to be that a group is the only group in its quasi-isometry class. Okay, so we say that H prime is virtually isomorphic to H if there are finite index subgroups J, I'll keep using my notation, H, J prime, H prime, and, okay, sorry, I have to finish the definition here. All right, definition. Okay, so I pass to finite index subgroups, and then maybe I need to quotient out by some finite groups. Okay, and finite normal subgroups. F and F prime, such that J mod F is the same as J prime mod F prime. Okay, so that's called virtually isomorphic. Okay, so some questions, and then we say definition. G is, we'll say like virtually X. Okay, so virtually something if G is virtually isomorphic to X. Okay, so let me give some examples here. Okay, and now we can talk about QI rigidity. So we say that H as a group is QI rigid Okay, I've stopped writing quasi-isometry and I'm always writing QI from now on. Okay, QI rigid if H prime is quasi-isometric to H, implies that H prime is virtually H. Okay, so we had some examples. Anybody remember the examples? I said, and then I said, I'll tell you what QI is later. No examples? Virtually isomorphic to X, yes. This means virtually isomorphic. Yeah, thank you. Let me write that down. Is virtually isomorphic to X. X could be a group. Yeah, I was trying to be vague. Let's make it virtually. I'll say C is virtually isomorphic to a group G prime contained in some class C. Okay, let's let C be a class. Okay, that'll make it a little, I was trying to be vague, but maybe I should be more. Okay, so anything? What's your favorite hyperbolic group? I haven't even said it today. What did you say? A surface group? That's your favorite one? That's right. So surface groups, very good. Hyperbolic surface groups. Are QI rigid. Okay, so if I am quasi-isometric to a hyperbolic surface group, like a surface of genus 2, then I am virtually a surface group of genus 2. So maybe you take a subgroup, maybe I have some torsion. Okay, so for example, the group that was right there, the right angle Coxer group, is virtually a surface group. Okay, so that's good. Okay, give me another example. Is there an easier example? 3 groups. And this, so Fn, okay, if I'm quasi-isometric to Fn, then I'm virtually Fn, and same for Z, okay, if I'm quasi-isometric to Z. In fact, if I have the same boundary as these are even more rigid. If I have the same boundary, then I'm virtually free. If I have a Cantor set boundary, or if I have, what's a boundary of Z? I didn't tell you. The boundary of Z, it's 2 points, good. Going that way and going that way, perfect. Okay, good. So these are all, so a lot of groups that we're familiar with are QI rigid. Okay, not, yeah? Yes, I'm about to say that. Very good, yeah. So, Cannon and Cooper. So hypervelicity, okay, wait. Let me say one more thing. Okay, so a class is QI rigid, if a property is a QI invariant if H is QI to H prime with the said property. Implies that H has the property. Okay, so I just want to define that. Okay, so I think what you just mentioned, so Cannon and Cooper, this is using work of Sullivan, showed in that if you have HQI to H3, okay, so now I wrote a group, which is called H, and a space, which is also called H. But what I mean is that if QH, so I can't talk about groups doing QI to spaces, I just mean it's QI to some group that acts geometrically on that space, sort of blurring them. So why don't I just say QI to G, G acts geometrically on H3, okay. Then H acts geometrically on H3. So then I can say acting geometrically on H3 is a QI invariant under QI. Okay, and then also closed n-dimensional hyperbolic manifolds. Is 2Q. And then more recently, I have a thing right here. Maybe this is a result you're alluding to. Helsinki-Lafleur. I'll just put quasi-isometric. Rigidity of three manifold groups. So if you're the fundamental group of a closed three manifold, okay, so you don't have to have a hyperbolic structure. Okay, you could be a graph manifold or the different manifolds. And then Beerstock and Neumann did some work classifying the different geometries into their quasi-isometry classes. A lot of work with this. Okay, so it's not true. So it's not true that, so one interesting fact, so cubulation is not a QI invariant. So being co-compactly cubulated, which someone will talk about, it could be me. I can at least say what it is in general not a QI invariant. Okay, so not everything is a QI invariant that you might hope for. All right, so let me talk just a little bit about CW complexes. So to try to get some more structure on our group, instead of just having a metric space and a boundary, we'll have kind of make it out of blocks. So if a CW complex I just build it out of the 0 cells and the 1 cells. I'll do the 2 cells. 2 cells, and I can keep going. So I take some 0 cells, which are just points. And then I take some 1 cells, which are just intervals. And I glue them to the 0 cells, and then I glue in a disk, okay, to make a cell complex. Okay, where I'm going to take the boundary of E alpha k is going to glue to Y to the k minus 1. You inductively build it up. I'm going to have continuous attaching knobs. Okay, so a GCW complex I'll just call it X tilde because that helps me, is a cell complex X okay, I'm going to want with a free G action. Okay, so I want it to free, like I also want it to be cellular. Okay, so I want it to take cells to cells. And I want it to not leave any cell invariant. And not take any cell to itself even. Just say it that way. Not take any cell to itself. Okay, so I'm going to want a free action. Okay, so a classifying space for a group for a group G, which we'll call a KG1. Is a CW complex X, okay, such that pi1 of this complex just equals G, and the higher homotopy groups are equal to 0 for all I bigger than 1. Okay, so I can also do this. I can just look at the universal cover, which will also be a cell complex. It'll be a one with a G action is equal to 0 for all I bigger than 0. Okay, so let's just do some examples. Okay, so I erased an example. So for this example, I forgot where I had the engineering. So for the free group, acting geometrically on this Haley graph, okay, when I map down, okay, this is a KG1. This X is a okay, this space is contractible. Okay, but, and we saw that this group acts geometrically on the space. However, if I did this, if I put these everywhere, so that it still was a nice action. Okay, this still is going to act geometrically on the space. It still has the same boundary. It's kind of the same metrically, but it's not the same algebraically. I'm going to get another little loop here. Okay, so this will not be, is not, okay, when I do that. Okay, but it's still actually, so that's sort of the difference between those two things. I want my space not only to be nice geometrically, but I want it to be contractible and nice topologically. Okay. Okay, so let's do some examples. Okay, so examples. So KG1 or Z is just going to be S1. So the cover is going to be R. Okay. Pi1 of a surface of higher genus. One is just going to be the, or It'll just be that surface. It'll be hyperbolic when it's higher genus. Okay, if the KG1 has one vertex, then the universal cover, the one skeleton of that is a Cayley graph. You can also construct it, just like I constructed the one for the free group. Okay, so we say that a group is type Fn. Definition. Fn if it has a KG1 with finite end skeleton. Okay, and notice that like F2 is finitely presented. And the cell complex structure will give it to me. So that's the main one that I'm going to be interested in. Okay, so some facts here. Okay, so facts, some hyperbolic groups. Are finite type. This is, so they actually met a finite K pi 1. So the universal cover of this is the Rips complex. Okay, however, they can have subgroups that are not a finite type. Okay. Okay, so in particular, they're finitely presented, which is what I'm mainly concerned with. It actually means a finite K pi 1. So it's not only Fn for all n, it's like finite dimensional itself. It doesn't, not only has finitely many cells, but the whole thing is finite. Yeah, I want torsion free, thank you. Thank you. Okay. And they still act geometrically on you can find a thing that acts geometrically on the Rips complex. Okay, so what was I going to write? Oh yeah, so in particular, they are finitely presented. Okay, so however, they can have subgroups that are not finitely presented and hence not hyperbolic. So however, finitely presented, it's not hyperbolic. Okay, so this can happen with hyperbolic groups. So let me just make a definition. Finitely presented, so I'll always start with a finitely presented group, is coherent if every finitely generated subgroup is finitely presented. Okay, so some examples of these include like z to the n, because they're, and free groups. So a free group, every finitely generated subgroup is actually free, so that's nice. Okay, and surface groups actually. It's not quite as obvious. It comes from the hyperbolic geometry in the hyperbolic case. And three-manifold groups. Okay, so this is even more non-trivial. This follows from Peter Scott. And looking at the finitely generated subgroups are going to correspond to a cover of the three-manifold, and that cover has a compact core, which allows you to get a finite presentation for these groups. So I don't mean to imply this is obvious at all just by writing it on a list. Okay, and incoherent otherwise. Okay, so oops, probably the best known example of an incoherent group is F2 times F2. So let's see how much time I have. 9 minutes. Okay, so I can think of this. So this equals like AB times XY. These are two free groups. So I can think of this as a free bicyclic group. Okay, so F2 times this Z, amalgamated along a F2 times this Z along the F2. So I can think of this as like ABX. So this is where I won't write that A, but A and B commute with X. Free product with ABY. So this is like F2 times Z and F2 times Z, amalgamated along their F2. Okay, and the subgroup, so if I'm incoherent, that means it's not true that every finitely generated subgroup is finitely presented. To show something is incoherent, you need to illustrate a witness to incoherence. Okay, so the witness here, so this is fiber. This looks like F2 times Z. And there's other kind of funny fibers that look like, say, AX negative 1 and B X negative 1. That's another fiber there. It's like I took the fiber and I tilted it by X. Okay, so I can look at this subgroup and this subgroup, BY negative 1. Okay, and they'll be kind of amalgamated along their intersection, which is just AB intersect AY negative 1, BY negative 1. No, I don't know if how many, do you want all these generators? Or I'll write it over here. They're amalgamated along their intersection. I won't even write it. It's hard to read. Do you want me to write over here? Okay, okay. Where should I stop the line, maybe? Put it here? Okay, I'll move it here. All right, let me write it over here. Yeah, do you want me to truncate it over here too? Now that I'm almost done with my talk? Right here, how's that? Should I stop here? Okay, that's good, so let's do this one. Okay, good. All right, so let me write the thing there. Okay, so this isn't a hyperbolic example, but I want to give this example because there's a hyperbolic example that's like it. So I have ABX. I'll just write this as F2 times Z. AB. Okay, I won't write all the relations. Okay, and then it's really like a fiber in here amalgamated with a fiber in here. So I have the fiber AX inverse amalgamated along their intersection with a Y inverse, BY inverse. Okay, so why am I saying, I just want you to get that this is a fiber and a fiber. Okay, so this is not a hyperbolic group because it's a product. I didn't tell you, but whenever you have a z plus z, it's going to kill hyperbolicity. And then you can, best be in a mouse, made a hyperbolic example. It's actually in H4. This is pi1 of a, it's inside pi1 of a hyperbolic 4 manifold. You can make it in a group that acts geometrically on H4. Okay, so remember I said all hyperbolic 3 manifold groups in general are coherent. So you take a fibered 3 manifold and another fibered 3 manifold, and you actually glue them together, not along a fiber, but along a different surface. They glue them along a totally geodesic surface. You can do it with a fiber too. They glue it along a totally geodesic surface. That red means totally geodesic. So what they do is they take one of those totally geodesic surfaces to be one H2 and H4, and then the 3 manifolds, one goes one way and the other goes the other way. So it's like 2 hyperbolic 4 manifolds glued along an H2. So this will be an H3 and an H3 glued along an H2. I said it actually geometrically in H4. They put this in a larger 4-dimensional hyperbolic reflection group. Okay, so this is incoherent because these 2 fibers glue together and their intersection is infinitely generated. Okay, the intersection of these 2 fiber subgroups along this totally geodesic surface is infinitely generated. So I have 2 finitely generated subgroups glued together along an infinitely generated subgroup, and that's infinitely presented. Okay, I'm not telling all the details because I'm almost out of time. And I wanted to say my question of the day, so I'm trying to tie this together. So an open question. An open question. So first of all, it's conjectured that all the hyperbolic 4 manifolds are incoherent, but I want to say that is incoherence itself a quasi-isometry invariant? Just to tie it back to quasi-isometry. Maybe you can restrict yourself to hyperbolic manifolds. I didn't say how it relates to the boundary. Oh, maybe I'll say one thing. So how is this related to hyperbolic spaces? So a subgroup H of a hyperbolic group G is quasi-convex. This is just one definition. If H quasi-isometrically embeds in G. So this, I can take any space that G acts geometrically on, look at the action, and then the orbit of the action of H should be a quasi-isometry from H here. Okay, so when this happens, so if H is a quasi-convex subgroup of G, then H is itself hyperbolic. And that's because you can look at the convex hull of this group and it'll act geometrically on that. Okay, and that'll quasi-isometrically embed into G. So it acts geometrically, H X geometrically on its convexal. Okay, which is a hyperbolic space. And also the boundary of H is going to embed in the boundary of G. So you can kind of see it as a quasi-convex subgroup. So now remember, hyperbolic groups are finite tight. So in particular, they're finitely presented. So if I have a quasi-convex subgroup, it can't be a witness to incoherence. So quasi-convex subgroups. Quasi-convex subgroups are finitely presented. And so we say something is locally quasi-convex. This means all finitely generated subgroups, I'm stopping, that's very good, are finitely generated, sorry, finitely presented. So that's going to imply coherent. Okay, so that's how this hyperbolic study can be related to coherence. But however, there are groups that are coherent, like three-manifold groups, that are not locally quasi-convex. Okay, and I'll stop there.
Any questions?
Yeah? Okay, so convergence group originally had, there's a lot of different definitions. So Tukey proved that that is equivalent to the definition where you have like a sequence of, if you take an infinite sequence of your group, then it has a convergent, it converges to something. So the definition that you might know, that definition is equivalent to the one I said about acting properly discontinuously and co-compactly on the space of triples. So Tukey, so convergence was not originally used for that definition that I gave you. So convergence group came from the action of a Kleinian group on its boundary and looking at the dynamics of that action. So that definition is equivalent to the one I gave. The one I gave is shorter and I think easier to comprehend. So that's why I gave that one. Yeah, so like for the Cantor set, it's not connected and the group is not one-ended. So there's not going to be cut points and it's locally connected. That's just a fact about hyperbolic boundaries. It's not true about relatively hyperbolic boundaries, which I didn't define. So I'm just saying that's notable. And those were notable facts to prove. They aren't obvious. And then if there's a local cut point, so when I remove the point, I have more than one end of my space, then that corresponds to having a splitting over Z. So it's also very non-trivial. That's work of Bowditch. Locally connected, yeah. Has no cut points. Uh-huh. Uh-huh. Oh, yeah.
Leftmost example.
This example?
Yeah. So I was looking at it and I'm like, okay, I have these 4 generators. And I'm like putting relations in it. And I need infinitely many relations. But that's because that's the obvious thing.
Yeah, that's right. So there's a lemma that I didn't say, many lemmas I didn't say, but there's one that says if I have 2 like finitely generated, finitely presented groups glued along an infinitely generated subgroup of them, then that is actually infinitely presented. So that's Neumann. It's not that hard.
That was a question actually, like, how hard is it to actually solve?
Yeah, I don't think it's that hard. It's in a paper of, I think, Peter Neumann, not Walter Neumann. I have to remember that. It's not super hard. It's algebraic proof.
You have 2 finitely
Yeah, then
together.
yeah, you're going to get infinite. There's no way to make that into a finite presentation. Yeah, and that is non-trivial, and I didn't say that, but it's a lemma.
That is non-trivial.
Yes, but it's not super hard. It's like I'll look it up for you. I'll find it. It's in a paper of Norman from, I don't know, maybe the 1960s or something. So it's like combinatorial. It's group theory.
So it doesn't use like spectral sequences?
No, nothing like that. No, nothing like that. Yeah. Oh yeah, that's a paper. Yeah. The quasi-isometric rigidity of three manifold groups. Yeah. Lisinski and LaCour. Yeah. Yeah. So it doesn't mean. So this just says if you're quasi-isometric to a three manifold group, then you're virtually a three manifold group. Not that you're cubulated. So it could be any three manifold group. You don't know which one it is. Just in the class somewhere. I think so. I'll have to go back and look at that. So Berstock and Neumann have a paper on quasi-isometric rigidity of the different geometries. I think there's two that are quasi-isometric to each other and they're cipher fiber spaces, but I think the cipher fiber space, I think that's true. I have to go look at that, make sure I have those things right. There can be funny things happening with H2, like the SL2R geometry and the H2 times R geometry. There's funny things happening with those cipher fiber spaces. So interesting things can happen with cipher fiber spaces.
Yeah, so let's thank the speaker again, and then